We're going to sponsor 2 projects this year. The second project has a name that I did not spend nearly enough time coming up with and just chose some root of some language. This is Project Volta, the automated variable load testing of a high voltage DC output board. So we're not going to get into the company stuff. You already know who I am. You already know the business. Might as well not be redundant. So let's get to the meat of it. As with any project, motivation. I already talked about our 1U blade UPS. It sells like hotcakes, but it is a serious challenge to assemble. Inside of that unit, there are over 20 different computer boards, printed circuit boards, all communicating with one another, sharing data. They're transferring power. There's so many signals, I can't even count them. And I can tell you, if you try to poke through, try to hit the bottom of that chassis, you will not succeed. It is a very complicated machine because we took something that was about this tall and made it that tall. So obviously, there are problems with that. Namely, trying to get everything to work the right first time. Now, this is what our sales team wants me to show you. It shows the pretty waveform. It shows a bunch of blocks you can't read, and then it's something cleaner on the outside. But we've already talked about cleaning it, so we're going to simplify it. Here's a UPS. Power factor correction, we clean our signal. It goes to a bus, and then we can go to a charger. We can go to the battery, an inverter, or what you guys are focusing on, the DC to DC board. I do have one of these boards sitting way back there, so I'm not going to get it. However, if anybody wants to see it after the presentation, you're more than welcome. So, the problem. This guy is 2 boards that kind of snap together. Just one single module. It's awesome. To test this to see if the board that we got from our board house is working or not, it's a lot. It's a lot. We have to partially assemble the unit every single time we want to test one board. There are controllers. There is a charger. We have the inverter board. We have the DC to DC board. I'm going to zoom in so you can just see how crazy this is. There's over 10 boards we have to make sure are connected properly, and all of them are working to make sure, that's the approximate location, to make sure that one module is working. It seems terrible. But when you make something awesome, sometimes you overlook these things at the beginning. But when your sales are going up, go us, and we need to ship more units, we need to do this faster, which means we need to make sure these boards work right off the bat. Meaning that we let the board house test them, but they don't know how, or we test them, and we have to do that. So, we're giving it to you. A functional prototype system capable of performing an automated load test of the 1U Blade's DC to DC output board. As with anything, there are caveats, requirements. You can't rely on any other system. I'm only going to give you the 2 boards. You can't ask for more. I don't take bribes. You need to be able to visually indicate to the operator the results of the test as well. Now, our operators, the people who are assembling these, they're not engineers. They're skilled technicians. They know their jobs. They can build these things blindfolded, but they just need to know. They don't need to know exactly why it failed right now. They just need to know this one's bad, this one's good, let's move on. But for us, we'd like to know the details. So obviously, this test that you're performing, we'd like you to log the data, collect it, and give it to us. I don't need a GUI. So the designers here, I'm sorry, you're out of luck. I just need the cold, hard data. Give me a CSV file, I'm happy. But let's break it down. Here's the main board. He gets 200 volts of DC power, DC voltage inputted, as well as 15 volts of auxiliary power. And there's a little enable pin right there that just tells him, hey, do your job. He outputs 28 volts DC, has a cap out right around 500 watts. It does this with the combination of using a lovely, beefy step-down transformer and what might have been covered in the electrical discipline. I only did half of it being a computer engineer. A DC to DC step-down converter using pulse width modulation. It's a mouthful. Show of hands, anybody know what that is? Yeah. Okay, it's in the curriculum. We're good. Awesome. Now this guy doesn't work, and we can't do that step-down without our Phet board. This guy just plugs right on into them. We have some beefy connectors right there. Now his job is really simple. He needs to step down 200 volts DC to 28. It does this through a series of switching and charging up of an inductor, and there's a controller chip on the main board that actually drives that. Because as different loads come in, that modulation is going to change because we need to get different waveforms so when we actually pass it, we get a better, cleaner signal. It also improves it. So me not being electrical, I learned about this project through our VP. And I was like, how do you reduce the voltage? I said, oh yeah, that's just a voltage divider. That's great. I know how those work. No. Because what happens? You just lose power. Through what? Heat. You want to know what you don't want to put in something that's supposed to withstand heat? More. So it's simple. Maybe. No, I do understand how it works. Don't worry, I am your technical director. Basically, it's a series of switching in which we're able to actually charge an inductor, cause a current path one way, and then when we turn it off, we can actually get a switch right there. We can see here, it might not be zoomed in. I don't think I got those in time. But we can see from our input, we're just going, whoa, made him disappear. Great. We're going up to off, up to off. But if you look at the output, and if we actually look at what's happening at that inductor, he's charging up, he's charging down, and we're actually getting a negative voltage. This allows us to get our signals to where we want it. It's higher level stuff. I'm learning as you are. Oh, I did zoom in. Beautiful. Great. Moving on, your guys' goal. I have two outcomes for this, one of which we've decided is well within the realm of Capstone, one of which we totally love. So if you're feeling like you want to put in that extra effort and get something done that's really going to help us out, stay tuned. The pass-fail is the easy one. That's your red light, green light. To do that, we're going to have to learn high voltage. I know the highest voltage we probably deal with here is like 12, maybe 13. So we're going to be using a 400 volt power supply, 200 volts DC. This isn't like zapping yourself with an outlet when you're trying to fix it. This is the stuff that can actually hurt. I've touched it. It hurts. So safety, obviously, major concern. We're going to have to learn how this board works. We have the schematics, we have the team, we understand how this all works. But if we don't understand how it works, how are we supposed to know how we're going to test it? What's a good board? What's a bad board? How does it act when it's good? How does it act when it's bad? I mentioned variable load testing. That's going to be a key part because this can support a wide range of loads. We need to know how it responds in one state, how it responds in the other, and be able to test that automatically. This is going to be your guys' choice. Either you guys can select input source in your variable load, or you can design one. You want to design a power supply? Go for it. Variable loads, we can get you some power resistors. They're these big beefy guys you can plug right on in. It's great, it's fun. You can get burnt by them though. And your sensing circuit, the actual meat of it. This isn't asking too much of an electrical engineer, we're just doing basic sensing of those same things I talked about in the previous project. But we need to be able to get some of that over for logging, so there is going to be a small CPU requirement. If you used an Arduino, you'll be happy. Then you're going to build it, test it, make sure it doesn't blow up, and give it to us. And you'll never see it again, unless you work for us. So our extended outcome is going to be figuring out the point of failure. Now there are these things, they're lovely, they look kind of creepy. They're called bed of nails testers, test fixtures. What these are is a massive thing. You clamp down, it's got all these points, test points. They go right down and they touch the circuits on that board. You can go from the bottom to the top, and what it's doing is sensing not just what's coming in and out like a black box. It now knows this is the one between that FET, that resistor, and you can actually start noticing that. So this is going to be the higher level analysis of how these converter boards work. We would love you guys to figure out one that can work at that nasty 90-degree angle that those two boards are in and can actually tell us what went wrong, because that's going to help us. Number one, because we can see what parts are failing, and if it's a vendor problem, we can change it. Or if we realize we didn't design it right, we can redesign the board altogether. That's something we do with a lot of our boards. This one of the 20-something is not one of them. It would obviously take a little bit more design, take a little bit more effort, and take a little more time, but provided the first part goes well, completely kind of within that extended outcome range, not what we're actually asking of the team. Obviously, I want to show you what we want first, in case anybody wants to try that hard. That being said, congrats. It's in your curriculum. That's all you need to know. I do have some requested skills, though. We do use LabVIEW, which is a very popular test automation system for all of our steps of the assembly process, whether that's testing the individual boards or the actual burn-ins where we take the thing up and we put it up to full output for 2 days and we make sure nothing goes wrong. It's pretty simple to use. It's graphical. We're going to give you a license. It would be great if you had experience. It's not required. We're going to give it to you and teach you. Experience databases or data logging. Databases, I can handle that after you give the project back. But if you want to do less work, do more work now so I do less work, that's great. Otherwise, just dump it out in a file and we can do what we want. And lastly, provided we don't decide to go LabVIEW and we just want to do this ourselves, it would be good if you had experience using some form of microcontroller, because that's how we're going to be getting some of these control signals out, changing what load we give, taking the data back. Your Raspberry Pis can talk to all those variable loads. It's a simple communication protocol. And obviously, you'll have help doing it. So do not fret. Don't be afraid of these requirements. They are not required. I don't expect the team members to have them. It's just, hey, if you do, awesome. We might get done quicker. That being said, I am still your technical director on this project. Still a software engineer. And you will have, obviously, the entire staff at Acumetrics behind you. So that being said, any questions?